welcome to Tuesday's edition of Cracking the Cryptic on another glorious spring day here in the UK. Now, what have we got for you today? On screen is a puzzle called Archer's Prison. And this is an unusual puzzle in that it's a collaboration. It's got two authors. So the authors are Wesley Murphy, who goes under the pseudonym Tirganus over on our Discord server, and Nitchant Agarwal, who goes under the pseudonym Nitchant Agarwal over on Discord. So the two of them have got together and created what is apparently a very, very smooth and beautiful puzzle. So we'll have a look at that in just a minute. A couple of things to mention. I mentioned it yesterday, but if you do own our THERMO SUDOKU app, make sure you keep checking for an update, because we've released an update, a couple of days ago. Loads of new puzzles on there. If your version doesn't update yet, it's just because the App Store or Google Play hasn't approved it yet. It has gone to them, so it should be any minute now. Also, of course, we've got our new, this video by Jovial, which we released on Sunday morning, in which he explains how he constructed the puzzle Syzygy. And I'm now getting lots of emails from constructors very interested in adding to that series. So I think there is going to be a series of videos where constructors show how to create Sudoku masterpieces, and that is something we can all look forward to. And then, of course, on Patreon, there's loads of extra stuff there. The most recent video we've put up there is my solve of Thomas Snyder's Gridlocked Sudoku. That's a classic Sudoku, quite difficult, but I found a bit of a hack for it, so you might like to watch that. And, of course, in just 2 days, it will be the start of April, and that means we get to release the sequel to Demono's Everything is Roggen puzzle. I know many of you are looking forward to that, and with good reason. So that is coming out just in 2 days' time. Right, that all said, let's get to the rules of this one. They're pretty standard actually. Normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage. So standard killer Sudoku rules. That means, for example, those 5 cells have got to add up to 19, and you can't repeat a digit. So you can't, for example, put 3 here and 3 here. Although that seems to accord with the rules of normal Sudoku, it does not accord with the rules of killer Sudoku when you can't repeat a digit in a cage. And also we've got arrows today, so digits along an arrow sum to the digit in that arrow's circle. Digits can repeat along arrows if allowed by the other constraints. So let's see if we got any examples of that. In fact, yeah, look, that cell, for example, if that was a 2, it would be fine for that to be a 2. That is possible because that doesn't break the rules of Sudoku, it doesn't break the rules of killer Sudoku, and it doesn't break the rules of arrows. So that's all good. Do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And a brief scan of the killer cages is not interesting, so maybe I will actually come back to the arrow I was about to use for the example there, because there are, this square is interesting immediately to me, because is it possible that these 4 digits are all different digits? Well, the answer is no, and in fact that arrow is the same, got the same geometry to it. You must have a repeated digit on this arrow, because 1 plus 2 plus 3 plus 4 adds to 10, and no matter how hard I try, the machine will not let me put 10 into that square. So we know that there's a repeated digit on this arrow. Those cells can't repeat because they're all in the same row of the Sudoku. So this digit here has to repeat in one of those 2 squares. And therefore it has to be a 1, 2 or a 3. Because if it's a 4 and you repeat 4, you'd have 8 in 2 cells on this arrow. The other 2 squares would be a 1 and a 2 minimum, and this would again break and be too high. And the same is true exactly down here, isn't it? Although this one is a bit more powerful, because this one, the repeated digit, actually those 2 squares have to be the repeated digit, because whatever's in here can't go in those 2 squares. So these 2 are the same, which means one of them is down here. I'm not sure if we know where. Oh, right, no, we can keep going with the arrows. So, another good question is whether or not there is a 1 in those 3 squares. Now, if there isn't, these 3 squares would have a minimum value of 2 plus 3 plus 4, which is 9. 9 plus whatever we put in this square breaks this total again. So there's definitely a 1. That's going to give us a 1 down here, I can see. There's definitely a 1 in one of those 3. There's definitely a 1 in one of these 3 squares. This highlighting is a little bit abnormal because I don't really like going across a box, but I think I will remember this. So now we know an 8 cage in 3 cells must include a 1. Again, same logic as here. 2 plus 3 plus 4 equals 9. So there must be a 1 here, and we have our first digit in the grid. And actually those 5 cells are now quite interesting to me straight away because they can't be that large. Let me just have a quick think about this for a second. Is there anything easier than that? So, why is it called Archer's Prison? Is this some sort of hint to what we're meant to be doing? I don't know. I'm actually not seeing anything else here. So I think I am forced to look at these squares. And my simple mind is just taking me to the fact these squares add up to 7. These squares have a maximum value of 8. And therefore, in fact, that's it, isn't it? There you go. So these have a maximum value of 8 because this cannot be less than 1 and has to be kept down. We've got to keep the overall total down to 10, or not to less than 10. So we've got a maximum of 8 here. We've got exactly 7 here. There are 5 cells here. So these 5 cells have a minimum value of 1 plus 2 plus 3 plus 4 plus 5, which is 15. So in fact, we now know that we can't keep these down lower than 8, because if we try to keep these lower than 8, we won't. These 5 cells together will add up to too small a number. We'd have to repeat one of the small digits. So these add up to 8. This must be a 1. This must be a 9, and we are. I was about to say we're cooking with gas, but unfortunately my pencil marks here are not helpful. I can't put 1 here because the 1 could go there. Okay, let's use my purple highlighting. Might as well. So those squares are now 2, 3, 4, and 5 in some order. So those squares are 6, 7, 8, 9 in some order. And ones. Do you need a 1 in a 19? Yes, you do. Oh, yes, you do. Ah, right. Okay, well, let's just come and have a think about 19 cages. So the question I ask myself is whether there is a 1 in a 19 cage. And the way to work that out quickly is to learn the triangular numbers. So I know that the triangular number for 6, by which I mean 1 plus 2 plus 3 plus 4 plus 5 plus 6, is 21. Therefore, if I was to miss out a 1 from the sequence of 1 plus 2 plus 3 plus 4 plus 5 plus 6, I immediately know that the minimum value the other cells can have is 20. Now 20 is, here is a knowledge bomb, greater than 19. So there must be a 1 in the 19 cage. Now this is interesting because now in this 19 cage, in fact this is interesting all over the place. In this 19 cage there must be a 1 there. In this 19 cage there's only one position now for a 1, which is here. And this one sees that square, which gets us a 1 here. So this is pushed up immediately now, because the minimum value of these 3 squares is 6, and the repeated digit is not a 1, it's a 2 or a 3. So this is 8 or 9. And I don't know if we know what that is. 1s have got to be in those squares, look. Oh, 1 in box 6. It's in one of these two squares. Well, it can't be in the circle of an arrow because it's not possible to sort of put, well, half and half into those squares. So the one goes here, the one goes here, and we can nearly finish the ones, but not quite. We're left with pencil marks in these dominoes in boxes 1 and 2. Right, where do we go now then? Hang on a minute. 4, 2. It is still possible that there's a 4 on these arrows. Okay, fair enough. It's not possible to put 5 on because then we will break once we repeat this digit. So 13. Okay, right. There's a bit of pressure on the 20 on this sort of W pentomino now, because these squares have a minimum value of 13. So these 3 squares have a maximum value. Oh yes, these have a maximum value of 10, and you can't put a 1 into any of them. So the absolute minimum I can make these squares is 2, 3, and 4. And the absolute maximum I can make them is 2, 3, and 5. 2, 3, and 5 obviously add to 10. 2, 3, and 4 add to 9. There is no other option. So there is a 2 and a 3 in these squares. My pencil marking today is dreadful in terms of how I would normally only put 2s and 3s, obviously, in the corner of cells when I'm looking at box logic. Here, it's all over the shop, but hopefully people can see what I'm intending. So this... If this is 9, this is 4. Right, so there's no 9 in here, because if the absolute minimum I can make these is 9, so the maximum I can make these is 14. Now if I have a 9 in here, the minimum I can make them is 15, so the 9's got to come out. So there's a 9 over here. So this either adds, it's either a 6-8 pair or it's a 6-7 pair. So there's definitely a 6 over here. There's no 6 over there. So now I've got a 2, 3, 4, 5 quadruple. Right, okay. I've got a 2, 3, 4, 5 quadruple, but I know I have to put a 2 and a 3 into 2 of these 3 squares. These 2 squares cannot contain a 2 and a 3 because that will break my 8 cage. If I put this 8 cage is either going to be 1, 2, 5 or 1, 3, 4. So if I put 2 and 3 into these 2 squares, neither of those becomes possible. So this square is a 2 or a 3, and that gives me a pair in box 4. So whatever this square is not here, but must appear in these 3 squares, so must be here. So this is lovely, actually. It's very clever the way this is working. So I've now got a 2, 3 pair here. So this is a 4, 5, which means this is a 2, 3 to make this add up to 7. I've now got a 2, 3 pair here. So this becomes a 4 or a 5. It's not a 2 or a 3. I think we can get rid of the 2, 3 pencil marks now. It's tempting to colour these. Is that going to tell me anything? If that and that are the same. Oh, actually, hang on a minute. That is interesting. Hang on, I am going to colour them. I've just noticed something. I don't think I need the 1s colouring anymore. Let us go back to colouring these 2s and 3s. So whatever this is obviously not the same as this. So it's the same as this. So these 2 are the same colour. Therefore, these 2 are the same colour. Now, the thing I was looking at initially was what the effect was on this box up here of these colourings. I don't think that's interesting, although I'll probably be proved wrong. But what is interesting is that this square we know has to repeat in these two squares. So one of these two squares is green. Now, where are we putting green in those three squares? We can't put it in the arrow because the minimum value for these squares is 5 because I can't use 1 on the arrow. So this square is green, which means this square is a 2 or a 3, which means one of these two squares is green, which means one of those two squares is green. So we are being extremely eco-friendly today. Now, what does that mean? And I don't know if you ever do this, but what I tend to do when I get something like this is to look at the digit that's most surprised me. This digit, being a 2 or a 3, has most surprised me. So this feels like where I should be looking. Is it something to do with the 19 cages? The 19 cages have some quite interesting geometry. Because of the positions of the ones, whatever goes in that domino can't appear. That's really interesting. Whatever goes in this domino here can't go. We can't fit both of these digits in this square. So this 19 cage has a different composition to this 19 cage. We can't use the same way of making 19 in 5 cells. Two, 3 here. So if this 19 cage has a 2 and a 3 in it, or has this green cell in it, would have to go here. Therefore, it couldn't go in this one. And if this one had this green cell in it, it couldn't go in that one. Is it possible both of them don't have a 2 or a 3 in them? Good grief, I've no idea. Don't think so. Nine, look. If we look at column 7 here, 9 hasn't made an appearance yet in column 7, and it's not in those two squares. Now that means 9 is in one of the 19 cages, and that for that cage, I don't know which one it is, but whichever cage contains a 9 will have to be 1, 2, 3, 4, 9, because the only way of making 4 cells add up to 10 is with 1, 2, 3, and 4. So one of these cages is 1, 2, 3, 4, 9. Does that mean, and that can't repeat in the other 19 cage? I'm not sure if I'm going down a rabbit hole here, but just bear with me for a second while I make a fool of myself in front of a lot of people. So if this one was 2, 3, 4, 9, this square would have to be 2, 3. That's interesting. Okay, I don't know if this is going to work the other way round. It is going to work the other way round, isn't it? Of course it is. It's almost exactly what I've just said. So what I'm thinking now is I now know that one of these cages is 2, 3, 4, 9. If it's this one, whatever this square is would have to go here and couldn't appear in this 19 cage. Now, if on the other hand this is 2, 3, 4, 9, whatever is in here has to be in here and couldn't be in there. So that means one of these cages has not got a green cell in it, and one of them does. So if green is 2, if you can't put 2 in a 19 cage, 1, 3, 4, 5. How are you going to make that work? 1, 3, 4, 5, 6 is the only way. So if there's no 2, if green is 2, the other 19 cage has to be 1, 3, 4, 5, 6. If green is 3, you can't put 3 in one of these 19 cages. So it would have to be 1, 2, 4, 5, 7. 1, 2, 4, 5, 7 is 19. Right, okay. So what does this mean? It means that one of these cages is 1, 2, 3, 4, 9. The other cage is either 1, 2, 4, 5, 7 or 1, 3, 4, 5, 6. So it has a 4 and a 5 in it. So, right, so there's 2 4s in these 19 cages. They must have a 4. So this square is not a 4. Is this all I'm getting from this? Because if you put a 4 here, you can't put a 4 in the other 19 cage, where we know both 19 cages have a 4. Let me show that. 1, 2, 3, 4, 9. 1 is either going with 1, 2, 4, 5, 7 or 1, 3, 4, 5, 6. Right, okay, I know how I'm going to use this now. I'm going to use this by noting there is no 8 in either of these 19 cages. So that means there's an 8 down here in the column. And that's useful because that means there's no 8 there, which means there's no 7 here. Bingo, bingo, got it. Now look, now these squares add up to 19. So that square must be a 4. Which means that's a 5, which means that's a 2. Now we know what green is. Green is 3. Green is 3. Good grief. So this now is 1, 2, 3. Because if once we know 3 is the repeated digit, we know, firstly, we know this is a 9. Secondly, we've got to keep this down now, otherwise we're going to break, we can't get to 9. So this must be a 2, 3 pair. 2, 5 here, so we're actually getting some progress. That's really clever as well, isn't it? The way that this 19 cage works. Once this 1 is locked here, it becomes, maybe that's why it's called Archer's Prison. I don't know, but it becomes very constrained how this 19 cage operates. Now we know purple is 2, so that's a 2. Get rid of these pencil marked 6s, pencil marked 9s. Why is these pencil marked? Oh, that's saying I've got 3 down here. Okay. Sorry about this. I'm just thinking. I'm sure eventually I will come to some logical deduction. 1, 2, 3. So this is a minimum of 4, 5, 6. That's 15. That's not interesting. 2 is in one of those squares. 3 is in one of those 3 squares. 7 is... oh, yes, now, this is interesting. 7 in this column now is not in those 2 squares because of this 7, 9 pair. So now we know there is a 7 in one of the 19... Well, we know there's a 7 in one of those squares. Ergo, there is a 7 in one of the 19 cages. Ergo, we know that's not the case, the cage that has 1, 2, 3, 4, 9 in it. So the other cage is 1, 2, 4, 5, 7. Therefore, what does that mean? 1, 2, 4, 5, 7. Hang on, sorry. I've now got one cage which is 1, 2, 4, 5, 7. One cage which is 1, 2, 3, 4, 9. So there are 2 2s. This is really clever. This is really clever. I have to say, I really admire what this weird arrangement of 19 cages is doing, because now I know there are 2 2s in here. Well, so in fact, what we can say now is that these squares, these 3 squares here, are a 2, 3, 4 triple. How do I know these are a 2, 3, 4 triple? Well, I've got a 3 here, so there's no 3 in those squares, but I know that there's a 3 in the 1, 2, 3, 4, 9 cage. So there must be a 3 in one of those 3 squares. There must be a 4, remember, in one of these 3 squares, because there are 2 4s in these cages. And we've just discovered there are 2 2s in these cages. So if there are 2 2s, this position here is not possible for a 2, because that would force only 1 2 into these 2 cages. So there's going to have to be a 2 in this column, and there's going to have to be a 2 in this row. And you can see, therefore, these 3 squares have to be 2, 3, and 4. And that is quite unusual. Like, that's not a 3 anymore, therefore. Have I got a 1, 3 pair there? Do I trust my pencil marks? Yes, I have. Oh, good. Okay, there's a 1, 3 pair up in the corner. We don't quite get the REM song until that is a 3. Oh, but the 2 now can't go here, because if this was a 2, whatever this is, this would have to be a double-digit number. So the 2 goes there. Which... okay, that doesn't seem to do anything. Right, okay, so what do we do next? 1, 2, 3, 4, so 5, 6, 7, 8 into these open cells here. I'm tempted not to pencil mark that, because I really... maybe this one, at least that sees 8. So this is 5, 6, or 7. Yes, yes. In fact, that is important, isn't it? Because this one, it's important for 2 reasons. Firstly, it's not 6, because I can't put 6 in here anymore. I've got 1, 2, 4, 5, 7, and 1, 2, 3, 4, 9. Oh, I see. So what? One good question would be, where does 6 go in column 7 of the grid? There must be a 6, 8 pair there. This is not 6, and this version of the 19 cage, because of this square, is not the 1, 2, 3, 4, 9 one. So these squares are, so there's definitely now 3 here in that domino, because this is the 1, 2, 3, 4, 9 one. What did I just do there? I'm not sure what I just removed. I think I removed the 4, and I don't actually want to do that. What I want to do is say there's definitely a 3 in here. There's no 3 here. And what I want to do is note that there must be a 9 in here, because we know this is a 1, 2, 3, 4, 9 cage. And, okay. 3 and 4 have got to go in these positions in box 9. That makes these 2 and 5. Do we know what this arrow is? Ah, beautiful, beautiful. Right, 2. Well, the question to ask is there a 2 on this arrow? And the answer is there must be a 2 on this arrow, because if there's no 2 on the arrow, this would have to be a 4-5 pair, because 1, 2 and 3 would not be available. If this is a 4-5 pair, this is a 9 and it would clash. So the 2s, which are in this row here, have to be on the arrow. There's a 2 here. That gives us a 2 and a 5. That means there is a 2 up there. Ah, it means this square is a 4. We've now got a 2-3 pair here, so this is a 4-9 pair. We can get rid of the corner pencil marks. There's no 4 at the top. This must be 2, 5 and 7 to complete the column. That's not 2, so we get the 2. And I feel like that was a big breakthrough. Maybe that's misspeaking, but okay, so this square now, wow, in fact, yeah, what can this square be? What can both of these squares be? You can't put 1, 2, 3, 4 or 5 in this square, and you can't put 7 in because that will put 9 here and that will break. So this is 6, this is 8. This 4 is giving us the 4 and the 3 at the bottom there. So those squares have got to be 5 and 7, which doesn't seem to be resolved, but that does tell us about the 7 and the 9. These 2 squares have got to be 3 and 9. That's not quite resolved either, and those two squares have got to be 6 and 8. Okay, so we've got lots of pairs all of a sudden. 3s. And we've actually used up most of the arrows. We've not used this arrow. 1, 2, 3, 4. So this has got to be, it can't be 8, 5, 6 or 7, I think. Right, this is interesting. Okay, so 5, 6, 7 here, 5, 6, 7 here, but this is removing 5, so that we get this down to 6 or 7. Oh, right, okay, and I tell you what it's not. It's not 6, because if it's 6, you have to do that. And now you've got a problem in that you've got at least 3 6s in columns 3 and 4. Now, in the finished solution, there will be 1 6 in that column and 1 6 in this column. There will be 2 6s in those columns. 1, 2, and a third one here won't work. So this is not 6, which means it's 7 apparently. And that doesn't do very much. Oh, no, it gives us a 7 in that box, though. So, sorry, I maligned the 7 needlessly. We've got 6, 8, and 9 is here, so the 9 must go here. This has got to be a 6, 8 pair. We know the top of the column must be a 5. That doesn't do anything. 9's in one of those squares. This has got to be 6 or 8. We've now got a 6, 8 pair here. So we need 2, 5 and 9 along the bottom. That's not 9. It's also... look, there's a 2, 3 pair. I hadn't noticed this in column 5. So that's resolved. And that's resolved. The 3 bounces back up here, and we play some pinball with 3s and 2s. That 2 plays pinball down here, and we get 9s. We get a 1, 9 pair now, I think. in this box, which are, so now we might do arithmetic here. We can use the secret. The secret, of course, being that if we were to add up those cells in the finished solution, we'd definitely be adding up the cells 1 to 9, which add to 45. So here we've got 15 and 17, that's 32. These have got to add up to, therefore, 13. So they are either, there's no 9 in them, so we're either looking at 5, 8 or 6, 7. Well, if it's 5, 8, it's going to have to be that way round, and if it's 6, 7, it's going to have to be that way round. Can anyone see if that's resolved? There must be a 4 in the 17 cage, which has to be in that domino there, which means there has to be a 4 in one of those two squares. Nines, threes, it must be about to crack, surely. Okay, and so now I get the feeling I'm missing something. What am I missing? Oh, maybe I do arithmetic on this box as well. I've got 13 there plus 18, that's 31. These have to add up to 14. So they're either 5, 9 or 6, 8. So if they're 5, 9, we know it's 9 here, 5 here, which might be possible. If it's 6, 8, it's got to be this way round. Ah, so now we know that there's definitely a 4 in this 18 cage. And that's interesting because these 4s are now aligning. So we found the two 4s that must exist in row 4 and row 5 of the grid. So this square's a 4. Although we can't have too many 4s. This square is 5 or 6. The 15 cage. I should have looked here. Those two squares add up to 10. So they can't put 1 there, or that's going to be a 9 and it will clash. So that's 3, that's 1, that's 7. I've been wondering how I'm going to disambiguate all the stuff at the top. But now I can understand how that is possible. So those squares there are 4, 6 and 8, which we can do. Well, we can't do all of it, but we can get the 4, and the 6, 8 will help us because that points 5 here, which we know goes with 8 to make 13. That fixes the 8 and the 6, the 5 and the 7. These squares now are 4, 6 and 7, and the 7 here is rather nice, isn't it? So all of those can go in. This column here still needs a 7 in it, so that must go there. That fixes the 7 and the 5. 5 is now in this domino. This square, 6 or 8, I think. We've almost pencil marked the whole grid. 5, 6 and 8 there. That looks correct. Okay. 5 in this spot. No. Hang on a minute. What have I missed here? This must be resolved. I can't see anything obvious to resolve this. Well, there's a simple point we can use to resolve it. I'm not sure if there's anything more elegant, but that square, you see the 9's in one of those two squares. If the 9's here, the puzzle breaks, because you have to, 9 here puts 9 here and 4 here. That makes this square a 4, but this square must be 5 to make sure this box adds to 18, and it can't be 5 because you'd have a repeated 5 in row 4 of the grid. So that cannot be a 9. Let's show you that slowly. 9, 9, 4, 4, 5. Boom. Problem. So we don't want problems like that, so we're going to make that the 9. That gives us the 9 and the 4, which forces the 4 upwards. And that means what now? Oh, those had to add up to 14, didn't they? So that also gives us a 5. That gives us a 6. Ah, there we go. 6, 8, 8, 6, 6, 8, 6, 8. 5 goes here. Those two squares. Yeah, we need an 8 in the box. So we go 8, 6, 6, 8. Click, tick. That's how to solve it. Very, very clever puzzle, actually. Very enjoyable. And that what was going on with the 19 cages, that is the thing that really I thought was very clever about this. I mean, it was elegant at the start. I loved the way the 1s went in, and I liked what happens with the 2s and the 3s. But this square being a 2 or a 3 and having to think through the options for the 19 cage, I'm not sure if I've missed something there, but I actually really enjoyed that, forcing one of them to be 1, 2, 3, 4, 9, and then working out the effect of the geometry on the other cage was lovely. So I hope you enjoyed it. Let me know in the comments as always, and we'll be back later with another edition of Cracking the Cryptic.